All right. Now, how do we? Well, we have seen exact differential equations, and we know that some differential equations are exact and some are not. And it would be good to know how we can figure out whether a given differential equation is exact or not. And there is a very simple check for exactness, right? So, what is an exact differential equation? An exact differential equation looks like this. If we have a potential u of xy, then an exact differential equation looks like the partial derivative of u with respect to x times dx plus the partial derivative of u of y with respect to u dy is 0, right? Well, but then uh, if we differentiate this with respect to y, then we get u x y. And if we differentiate this with respect to x, we get u y x. And we know that the second mixed partial derivatives should be equal. So, and if this, it means that if this is something like m and this is something like n, then if our differential equation is exact, then the partial derivative of m with respect to y equals the partial derivative of n with respect to x. Okay, now it is a bit harder to verify that the converse is also true. So what if we have our differential equation, and then, well, it tells us that if we differentiate m with respect to y and n with respect to x, and if we get different answers, then our differential equation is for sure not exact. But what if we get the same answer? So is it true that there is always a potential function that produces this differential equation? And the answer is that it is a bit tricky. So it is going to be true, but only in a so-called simply connected domain. Now, I'm not going to explain this in full detail, so what a simply connected domain is. So I think you can just, if you're interested, you can just Google it out, right? So, but basically, a simply connected domain is something that does not have holes. So like here, R is a simply connected domain, but this, well, in A, sorry, A is a simply connected domain, but B and C are not simply connected domains, right? So something like an annulus, something with holes is not simply connected, but something without holes is going to be a simply connected domain. So, and frankly, this is kind of a very, so the reasons for that are quite deep. So to prove it, you need to introduce, well, a lot of really complicated mathematics. But yeah, well, that's the fact. All right. So here is the first example. So is the following differential equation exact? Now let me here assume that both x and y are positive. So x is going to be positive and y is going to be positive. Just for simplicity, right? So in that case, my m is going to be 1 plus logarithm of the product is the sum of logarithms ln x plus ln y, right? And this is my n. So n is x divided by y. Now, in order to test for exactness, yeah, so I assumed that both x and y are positive because the domain of my left-hand side of my different, well, yeah, the left-hand side of my differential equation is now the first quadrant, which is simply connected. Now, how do we test for exactness, right? So we differentiate m with respect to y, and we differentiate n with respect to x. So the derivative of n with respect to x is 1 over y, and the derivative of m with respect to y is also 1 over y, and they are equal. So the answer is yes, this differential equation is exact, right? And if you want to figure out what the potential is, you kind of, it's doable, so you have to integrate ln x with respect to x, and you'll have to integrate x over y with respect to y. Yeah. Okay, next example. So is this differential equation exact, right? So let me do it quickly. So I take this is my take this. This is my n. Now I differentiate m with respect to y. The answer is x squared. Then I differentiate n with respect to x, and the answer is minus y squared. And they are not equal. So, and since they are not equal, the answer is no. This differential equation is not exact. Okay, and there is one more example. So here, not only I'm supposed to verify that it is exact, but I also need to find a general solution. Well, uh, I mean, you can guess that since at this point in the lecture, um, I haven't explained how to solve non-exact differential equations yet, right? So it means that in order for this to be solvable, it has to be exact. So, and of course it is exact, but let me just explain how we can again verify that it is exact. So if this is m, so the derivative of, of m with respect to y is going to be 2x e to the y. And if this is n, then the partial derivative of n with respect to x is going to be 2x e to the y plus cosine y doesn't have x, so that's it, and they are indeed equal. So this differential equation is exact. So notice that here x and y can be any real numbers, so the domain is just the whole plane R2, and the whole plane is simply connected because it does not have holes. Okay, so this differential equation is exact. Now, how do we solve it? So to solve it, we need to find the potential, right? So if this is 2x e to the y is in fact the derivative of some unknown function with respect to x, it means that my unknown function u is the antiderivative 2x e to the y with respect to x, right? Differentiating this with respect to x, I will get x squared e to the y plus some constant. Well, if you had a function of just one variable, then you would stop here. But we have a function of two variables, right? And strictly speaking, for different values of y, my constant could be different, right? So it should really be a constant that depends on y. So it's not really a constant, but a function of y, right? Because now you can imagine that if I want to differentiate this form, right? So differentiating this with respect to x, I'm going to basically kill this c of y, right? So which will give me the correct partial derivative with respect to x, right? So now the partial derivative of u with respect to y is going to be x squared times e to the y plus this c of y, this function c differentiated with respect to y. So I was just trying to see c prime of y. And this equals my coefficient in front of dy, which is x squared e to the y plus cosine y. All right, so x squared e to the y on the left hand side, x squared e to the y on the right hand side. So cancels out, so c prime of y equals cosine y. So which means that c of y itself is going to be the antiderivative of cosine y dy, which is just sine y. So, and the answer is that my potential u is going to be well, x squared e to the y plus c of y, which is sine y. And the general solution of the differential equation is going to be this thing equals some constant c. Now, if we wanted to express y as a function of x, then we wouldn't be able to, because you can't really solve this equation for y. But if you want, you can solve it for x, right? So, and then you will express x as a function of y, right? So if it is required, then you could solve for x. Solve for x, right? So because moving sine y to the right hand side and divided by e to the y, you will get x squared equals c minus sine of y divided by e to the y. So which means that x itself is going to be plus minus square root of this c minus sine y divided by e to the y. Okay, so that's the answer. But again, so if it is kind of required to express it in closed form. So here it is impossible to express y as a function of x in closed form, but it is possible to express x as a function of y in closed form. And that's it about the test for exactness.